So like I said, practice test will be on Wednesday, so try and maybe dig that one out in the next 2 days as well. 8-1, 8-2, and 8-3. And if you're trying to remember what on earth we learned from those sections, 8-1 was about direct and inverse and joint variation. What's the only one we do division for? Only inverse is division. Everything else is multiplication. And then 8-2 was about graphing when we have everything in this perfect y equals a over x minus h plus k format, which didn't end up being too difficult either because we know a lot about a, h, and k. So now 8-3 says rational functions and their graphs. And hopefully you're thinking, well, didn't we already do that? We did, but I had mentioned to you that at college there's like 3 different classes: hyperbolic functions 1, hyperbolic functions 2, hyperbolic functions 3, because there's so much you can do once you involve division with your graphs. So not all of them are going to look like our perfect y equals a over x minus h plus k, but we still have to graph them, and we still want to know a lot of the important parts of them. So today we're going to start identifying properties of rational functions and graphing rational functions. And rational functions they're one of those things that show up a lot when you're trying to do statistics for things like ball games. So last season you made 40% of your basketball shots all together. And the game 1 shot chart shows that you did not start this season so well. Let's see, we've got 1, 2, 3 little greens over, I counted this earlier, what was it, 16? Yeah, 16 total shots. So you're definitely not at your 40% that you were last year. Starting with game 2, how many consecutive shots must you make to raise your percentage to 40%? Well, here's what we know. You only made 3. You're going to take some more. We don't know how many more. And we know that right now you have 16, but you're definitely going to take the same amount of shots, you know. So we've got this 3 plus x over 16 plus x, or you could switch them around and do x plus 3 over x plus 16. But what you want to happen there is that comes out to be 40%. And we know we don't put percentages into our formulas. We have to change those into a decimal. Now, we could just use a calculator at this point and do y sub 1 and y sub 2 and see where they hit each other. But today, what I want to do is the stuff we could do by hand, things that we could figure out without having to grab a graphing calculator to get these in. And this is how we start. We will use a ratio of polynomial functions to form a rational function. So the reason I go through that problem is so that you can see this is division. There's division taking place here. Rational function, the root word of rational is ratio, and ratio means fraction. That's exactly what we have. Now, if I'm going to put this into a calculator, I have to use parentheses for both the numerator and the denominator because there's more than one term in the numerator and there's more than one term in the denominator. And we'll get to the part where we're plugging stuff in with the calculator, but that'll be tomorrow. So essential understanding, if a function has a polynomial in its denominator, its graph has a gap at each zero of the polynomial. The gap could be a 1-point hole in the graph. That's something you've never experienced before. That's going to be new today. We could have an actual hole in our graph. Or it could be a vertical asymptote. Now, in this case, the number that would be bad down here is negative 16. And I'm going to flat out tell you that would be a vertical asymptote in this graph. But what we want to do today is figure out, well, how are we going to know if they're a hole or if they're a vertical asymptote? And what are a lot of things that we can know about this graph before we put it in the graphing calculator? Because when we have parentheses going and what we have to put in the graphing calculator, people make mistakes. Sometimes people forget to put the parentheses in. They get a graph that's totally wrong. And if they don't know any of the things that were supposed to happen, they're not going to know that their graph is wrong. So we want to make sure we can do parts of this by hand. So here's how it starts. You have some rational function that we can write as some polynomial over some polynomial. That's what we want to do. P of x and q of x, polynomial functions. The domain of f of x is all real numbers except the one that would make our denominator 0. Now, we already did that on Thursday and Friday of last week. We said, hey, you can't have zeros here because you can't divide by 0. So down here, we're going to see some rational functions. They use division, and then they're going to give us some information about them, and we're going to hope that we can figure out why it worked that way. And here's where I said there's 3 whole classes in college about these. Each one of these has something very different happening. If we look at this first graph, we might say, how am I supposed to know that's a hyperbola? Those aren't really 2 branches. They kind of meet at this one spot. But it's so unique that something like division would have to take place to make it look that way. What is up here? Look at that business. There's a hole in this graph. Well, we better look at that in a little bit and figure out why that one has a hole. This looks like what we've been doing. This looks like Friday and Thursday. So that we'd feel a little bit more comfortable with. So why did this happen the way that it happened? Well, if we look at this first one, we see this isn't an x to the first over an x to the first anymore. So there's more going on because they raised the power here, and it's x squared over x plus 1. And I think, okay, to get asymptotes, we have to see where the denominator is 0. So x squared plus 1, let's see. I would need 2 numbers that multiply to 1 and add to 0. Well, 1 and 1 add to 2, and negative 1 and negative 1 add to negative 2. I can't factor that. But I can figure out when it's 0, because I could just set it equal to 0. So I could subtract 1 from both sides, take the square root. Oh, wait a second. What's the square root of negative 1? It's I. So that's why this one doesn't have any vertical asymptotes, holes, or anything goofy, is because it has imaginary stuff in the denominator. And we can't graph imaginary stuff. We graph on the real number plane. Now I'm really interested in the second one because I want to know, why is that hole there? And that hole pretty obviously is supposed to be at negative 2, so there must be something about this that's supposed to tell me that there's a hole. Let's see. Oh, well, no, that would make it a vertical asymptote if we put negative 2 in there. Negative 2 plus 2 is 0. But wait a second. This hasn't happened before. If we were to continue on doing algebra with that one, what would we do with the x plus 2's? We would cancel them out. So if we can cancel, then we get holes. Now, if we want to figure out where that hole is, we actually do the canceling. So we would cancel out the x plus 2's and get x plus 3. Now, we know the hole is supposed to be at negative 2 something. That something comes from putting negative 2 into x plus 3. Negative 2 plus 3 is 1. And there it is, right there. So if it cancels, it's a hole. Now, this one has a nice vertical asymptote. Well, that's because this isn't going to cancel. Nothing we can do there. So this is normal. Our vertical asymptote is where x equals 2, because that would make it a 0 in the denominator. So what we just found out was these could get a little weird. They may not look as nice and perfect and symmetric as what we've seen in the past. And if we have something that could cancel out of the numerator and the denominator, that creates a hole. And I'm going to tell you right now, graphing calculators do not show holes. Graphing calculators are built to try to connect things. So if we put this in our graphing calculator, we're not going to see a hole. We won't know that. So we have to know that part before we start. It has to do with the canceling. So this was about holes in vertical asymptotes, and those come from the zeros of the denominator. Now remind me, how are you going to know a hole when you see it? It will cancel. Not the vertical asymptotes. They're not going to go anywhere. They're going to stay put. Now that first graph that we see up there, and I always think this is another part where with hyperbolas we get to see how useful this is for things like animation. This is how they make seagulls off in the distance. Remember Finding Nemo? Seagulls off in the distance, they just look like this kind of curved piece with the wings. That's how they make them, is by using hyperbolas to get those things going. So that first graph is called a continuous graph, and that's because when you draw that graph, your pencil will never leave the paper. There are not two separate branches for that graph. John, can you get your packet out and take notes, please? Do you have your packet? Otherwise, you could take some notes on notebook paper. Alrighty, has no jumps, no breaks, no holes. Those are continuous graphs. The second and third, they have some weird stuff going on. We had a hole in the second one, we had a vertical asymptote in the third. Those are called discontinuous graphs. And wherever the graph is not going is called a point of discontinuity. Where does something strange happen? Where do you have a hole? Where do you have a vertical asymptote? And then you have to know which one is which. And we've already determined it's not hard to tell. If it cancels out, it's going to be a hole. If it doesn't, it's a vertical asymptote. So, like I said, they have this fancy name for the vertical asymptotes and the holes. They're called points of discontinuity. Now I want you to remember that to be a continuous graph means you never lift up your pencil when you draw the whole thing. From arrow to arrow, never lift up the pencil. So discontinuous, we definitely saw in the second one, because you'd get to the hole and you'd have to lift your pencil and make a little donut hole and then go up. And definitely in the third one, we had a vertical asymptote, for goodness sake. Two separate branches. You had to lift your pencil to graph that. So, if a is a real number for which the denominator of the rational function is 0, that's where we know the problem comes from. You can't divide by 0. Then a is not in the domain of f of x. The graph of f of x is not continuous because it either has a hole or a vertical asymptote at x equals a. And that's, again, called, fancy name, point of discontinuity. Now, we're not going to write down point of discontinuity every time we want to talk about this because this is math, and in math, we hate writing out words. So we're going to refer to these as pods. The PODs, points of discontinuity. We want to know where they are, and we want to know, is it a hole or is it a vertical asymptote? Now, this one is the equation that they had for the second graph that we looked at. And we looked at this and said, okay, x plus 2 would cancel. That's why this was a hole. So this one has a removable discontinuity. A hole is called a removable discontinuity. Why? Why does that get that special name of removable discontinuity? Well, because if we wanted to, we could find something to fill that hole. It's just a hole. We could tell somebody, graph this point, and in the graph that we did, it was 2, 1. And then your graph will be continuous. It'll keep going. So it's a removable discontinuity because it's a donut hole. We could put custard in there, fill up the donut hole. Put some raspberry jelly in. People like that. The hole in the graph is called a removable discontinuity because if we said at -2, oh, I forgot it was a negative. At -2, graph 1, we could fill it up. But this one, there's not a little hole that we could fill up. This is a vertical asymptote right here. So the graph of x plus 4 over x minus 2 has a non-removable discontinuity. That's a vertical asymptote. Vertical asymptotes are not holes. Vertical asymptotes keep going forever. We can't just fill it in with the custard. It isn't going to happen. So no way to redefine it. So holes have a fancy name of removable discontinuity. And vertical asymptotes have a fancy name of non-removable discontinuity. So you might want to do this to make it easier to look up in your notes if my blue starts working here. Holes are removable discontinuities. Vertical asymptotes are non-removable discontinuities. There's an actual branch on one side, branch on the other side. Filling in the whole donut hole with custard is not going to help at all. So what do? Well, it was really easy to see that the holes were going to cancel because they were factored. So that's what we have to do. To find the zeros of the numerator and denominator, definitely, if you can factor, factor first. Get that done. The discontinuity caused by whatever factor it is to the nth power in that denominator is removable, which makes it a whole, if we can cancel it. Now, this is how that's said in fancy math speak language. You see an x minus a to the n on the top and an x minus a to the n on the bottom, and you go cancel, cancel. Then it's a whole. So problem 1, we're just going to find the pods, points of discontinuity. And then we're going to talk about the domain and how all of this comes together. So what are the domain and points of discontinuity of each rational function? Are those points of discontinuity removable, making them a whole, or non-removable, making them a vertical asymptote? And then they've added one other piece here, which we used to do a lot, which is find the x and y intercepts. We might be a little rusty on that, so we'll have to scrape the rust off and remember how to do those. All right, I'm looking at A, saying to myself, that numerator is already factored. There's nothing I can do there. But I wonder about that denominator. Greatest common monomial factor? No. Perfect square trinomial? No. Good old-fashioned factoring? Are there two numbers that multiply to positive 3 and add to negative 4? Yeah. So now, it says do this in this order. Talk about the domain. What x's are out? 1 and 3 are done. So x can't be 1 and x can't be 3. So we say x is not equal to 1 and x is not equal to 3. Points of discontinuity. Well, that's any zeros that we have in the denominator. Well, we just said those were at 1 and 3. Are those points of discontinuity removable or non-removable? Well, either of those two cancel. Both are non-removable. Both are non-removable, which makes them vertical asymptotes, by the way. They didn't ask that, but I'm going to go ahead and put VA right here. And then, like I said, we haven't had to do this in a while. Find the x and y intercepts. All right, the x-intercept. So the x-intercept is going to be some number 0. So that means y has to be 0. Well, the only way y is going to be 0 is if x plus 3 equals 0. Because the denominator is for wholes and vertical asymptotes. But the only way to get a 0 is going to be a 0 on the top. A 0 on the bottom is undefined. So when is x plus 3 going to be 0? When it's negative 3. There's our x-intercept. The y-intercept. If you want to graph something on the y-axis, it's 0 something. This one's a little easier because we know how to do this already when we've been making tables. We just put the x value in wherever there's an x. So we're going to put in 0 plus 3 is 3. 0 minus 0 is 0, plus 3 is 3. 1. So to get the x-intercept, you have to figure out when is the top of this fraction 0. We haven't had to do that for a while. We've been talking a lot about the denominator and getting that to be 0. But there it is. We did all the stuff they wanted. Domain, points of discontinuity. Both of them are non-removable because they're vertical asymptotes. And we've got our x-intercept and our y-intercept. All right, let's go to B. X minus 5. Can we factor that anymore? That's done, huh? How about x squared plus 1? Can we factor that? Well, let's try. Two numbers that multiply to positive 1 and add to 0. Can't happen, can it? This is the one I did on the last page where I said, all right, backup plan. Let me set that equal to 0. Uh-oh. Those are imaginary. We don't get any zeros in the denominator. There's no way to factor that. So now, what are the domain? All right, domain. If there's no way to get a 0 in the denominator, what does that mean? All real numbers. Yeah, there isn't anything that's going to be a problem. It was imaginary, and we can't graph imaginary. Then we need our pods. Points of discontinuity. Do we have any holes? Any vertical asymptotes? No, because we can't make our denominator 0. So this is none. We don't get any. So we don't get to tell them whether or not they're removable or non-removable. But might be a pretty good chance that we can tell them an x-intercept and a y-intercept. So remember, the x-intercept is something 0. So y has to come out to be 0. So let's go back up here. 0 will have to be equal to x minus 5. So what number will work for that? And then the y-intercept again is easier because we're going to put a 0 in for the x's. 0 minus 5 is negative 5. 0 plus 1 is 1. There it is. We've got a couple of points that we could graph for that one. 5, 0, and 0, negative 5. Let's go to C. X squared minus 3x minus 4. That looks factorable. Let's see. There's no greatest common monomial factor. It's not a perfect square because that's a negative 4 back there. It's not a perfect square trinomial. Do we know two numbers that multiply to negative 4 and add to negative 3? Is that denominator factorable? All right, so it looks like we have one number that's going to be bad news for our domain. What's that number? A 4. X can't be 4. Now we have to figure out if that's removable or non-removable. Will it cancel? Oh, it will. This one is removable. Oh, shoot, I forgot to put pods down first, then removable. So our pod pretty obviously is at x equals 4, but it is removable, which makes it a hole. And I'm having trouble spelling removable. Come on. There we go, blue. And that makes it a hole. Now, we need a little practice in finding the coordinates of a hole. So, we're going to go ahead and figure out where this hole would be. and it's going to be at 4 something. How we find the something is we actually do the canceling. Does everybody see that x minus 4 would cancel out here? So we do the canceling and we get a new little formula. X plus 1. What's 4 plus 1? So now we already know where the hole is going to be. It's going to be at the ordered pair 4, 5. All right, domain, pod, removable. It's a hole. X-intercept, something 0. Y-intercept, 0 something. So let's take a peek. We now have 2 numbers that could make the top of this fraction 0. What would the numbers be? 4 and -1. But wasn't there something special about 4? Yeah, it cancels. It's a hole. So it can't be an x-intercept. So we just have to take -1. That's where it's going to cross. And now we'll go take our 0 and put it in for the x's. 0 minus 4 over 0 minus 4. Hey, that's 1. So not only did we find some stuff that won't show up on the graph, but we're finding some things that will show up, the x-intercept and the y-intercept. That's it. Yes. Yes. The thing I'm not doing here, because I want everybody to see all the parts, is I'm not actually doing the canceling as we go through there. So as long as you keep going and put that that's going to be what it is when you cancel, then you can just use that to get your y-intercept. All right. Away we go. So now I need more of you and less of me. What are the domain and points of discontinuity of the rational function? Are they removable or non-removable? And then x and y intercepts of the rational function. So the first question I have for you is, when you look at A, does any of that appear to be something you could factor? Oh, which one? Denominator? How does that factor? All right, so give me a number or numbers that are out of the domain. So where are the pods? Yeah, -4 and 4. Are those going to be removable or non-removable? They're not going anywhere, are they? There's no canceling those out. So are they holes or vertical asymptotes? Yeah. Well, we're already down to x and y intercepts. All right. The x-intercept comes from y being 0. Uh-oh. Is there some kind of magical math where 0 equals 1? That means we don't get an x-intercept. It's never going to cross the x-axis. But I think we have a place we can put the 0 in for x. What little fraction would we get if we do that? -1/16. Yep, got it. Oh, B looks interesting. Numerator factorable? What does that factor into? X plus 1 and x minus 1. Is that denominator factorable? Well, let's check for sure. X squared plus 3 equals 0. X squared will equal -3. Uh-oh. Yep, this is imaginary again. I squared is 3. Nah, that's not real. All right, so x squared plus 3, there's nothing we can do. So now, domain. Any numbers out? No, it came out to I squared roots of 3. Are there any real? Yeah, all real numbers. There aren't any real numbers we can't use. It was imaginary stuff that we got. So if that's true, do we have any pods? No. So we can skip ahead to x-intercept and y-intercept. What number or numbers will make the top of this 0? -1 and 1. And looking right here, you can see those are the 2. So we actually get 2 x-intercepts in this one. Now go ahead and put your zeros in for the x's. I need the little fraction you'll get. What's the little fraction? Yep. Now, I'm sure I wrote too big, but let's try and squish this last one in here. X plus 1, nothing we can do there. But let's at least try to factor that denominator. There's no greatest common monomial factor. It's not a perfect square trinomial, but do you know 2 numbers that make it work? 2 and 1. So, domain-wise, what's out? So then those must be our pods. And now we have to talk non-removable or removable. First of all, is either one of them or both removable? Oh, which one's out? Okay, so these are going to be removable. I'm just going to put REM for this one. And I'll put NR for the other, for non-removable. So the removable one on the graph would actually look like a what? A hole. And the other one would be a vertical asymptote. And now we need x-intercept, y-intercept, so what number would make our numerator 0? Except, wasn't that a hole? So that can't be our x-intercept. We're not going to get one. It's already a hole. All right, y-intercept. Put your zeros in. What do you get? 1/2. 0 plus 1, 0, 0 plus 2. And we have them. So already we're finding a lot of things that either aren't going to show up on our graph or are going to show up on our graph before we even grab a graphing calculator. If a rational function has a non-removable discontinuity at x equals a, those are the vertical asymptotes. And again, those have to go on our graph immediately. We get those vertical asymptotes on there. If it won't cancel, it's a vertical asymptote. And we put it on there. So the rest of this isn't really new. It's just reminding us that, hey, if this cancels, it's a hole. It's not a vertical asymptote. And that's what this says right here. The graph of the rational function f of x equals p of x over q of x has a vertical asymptote if it has no common zeros. Those common zeros are things that we would factor out. So if p of x have some factor x minus a to the m and x minus a to the n, we cancel those. Those are holes. But anything that's left down in the denominator, that's going to be a vertical asymptote. So look at problem 2. See anything that's going to cancel? Well, and that means we have some vertical asymptotes. Where are they? Yeah. Now they're lines, so we have to write x equals 2 and x equals 3 because they're vertical lines, and those are equations for lines. Well, that was a whole lot of space for nothing. That's all we had to do. We didn't even have to factor that one. Well, it looks like these first two are going to be a piece of cake because they're already factored. So take a peek at A. Any canceling? So no holes. Where's the VAs? Yep. Take a look at B. Any holes? Yes. We don't want that one. They only want the vertical asymptotes. So which 0 is not going to cancel? That's the one. Now C is not factored yet. The numerator has not been factored, and they did that on purpose. What does x squared minus 1 factor to? So is the one thing we have in the denominator going to be a vertical asymptote? Nope. It's going to be a hole. So this we'd have to put no VA. And that is a fantastic place. Let's fill this one little box. A rational function can have any number of vertical asymptotes. They can put as many zeros as they want in the denominator, but no more than one horizontal asymptote. But we've learned a pretty good chunk of stuff today. A lot of it review, one new piece. How do you know that an equation has a hole? There it is. And I will give you some graph paper because the review has you doing some graphing. But notice this 13 to 22 part here, I'm not having you do any graphing. You are just doing the identification that we did today. So it's going to be, do you know a hole when you see it? Vertical asymptote. They won't even ask you about vertical asymptote.